Hi, students and friends. This is your host and teacher Sayyid Ayazuddin Haider. You're watching Learn and Teach by Sir Ayaz. So I will continue my video session for 0620, and for this video I have selected the variant 62 and it's of May-June 2023. So here's question number 1. Hot powdered lead to oxide is reduced by methane, a flammable gas. The products are lead, steam, and carbon dioxide gas. Figure 1.1 shows the apparatus used to reduce lead to oxide using excess methane. Here we are having powdered lead to oxide. This is lead to oxide, and there is a methane gas coming from the left hand side. So any gases produced will be collected in this ice containing container, this container A. So waste gases are removed on the right hand side. So in A, name the item of apparatus labeled A. It's a beaker. So you write beaker. B, draw an arrow on figure 1.1 to show where the apparatus should be heated. Now here, lead to oxide must be heated. So you can draw the arrow in this portion like this. C, explain why powdered lead to oxide is used and not a large lump of lead to oxide is used. Definitely powder reacts faster because it has large surface area. Powder reacts faster or has large surface area. D, explain what happens at point labeled B on figure 1.1. What is happening here? Here's the ice. It is definitely cooling down the vapor coming from this. And what vapors we are receiving? We are receiving the vapors of steam. So it's cooling down the steam. So what you write? Ice cools steam. Ice cools steam or vapor. Then water is forming. Water forms, or you can write, or steam condenses. In the test tube. E, the waste gases contain methane. State why the waste gases should not be released into the laboratory. Gas is flammable because one of the gases, methane. Gas is flammable. It's better to mention the name of the gas here, methane. Moving to next question. Number 2, a student investigates how the rate of the reaction between aqueous iron nitrate and aqueous sodium thiosulfate changes with temperature. The student does 5 experiments using the apparatus shown in figure 2.1. You see the figure? Figure 2.1, at the bottom you have a printed sheet. It contains some printed text, and there's a beaker, 100 centimeter cube of beaker, which contains 50 centimeter cube of aqueous iron 2 nitrate, and on top they're adding 5 centimeter cube of aqueous sodium thiosulfate, and this is observer. Here we have observer. A, experiment 1, use a 50 centimeter cube measuring cylinder to pour 50 centimeter cube aqueous iron 3 nitrate into a beaker. Stand the beaker on a printed sheet as shown in figure 2.1. Use a 10 centimeter cube measuring cylinder to pour 5 centimeter cube aqueous sodium thiosulfate into the beaker, and at the same time start a stop clock. Use a thermometer to stir the contents of the beaker. Look down from above the beaker, and when the text on the printed sheet becomes visible, stop the clock. Stop clock. Use the thermometer to measure the temperature of the solution when the text becomes visible. Rinse the beaker and thermometer with water. Experiment 2. Use a 50 centimeter cube measuring cylinder to pour 50 centimeter cube of aqueous iron 3 nitrate into the 100 centimeter cube beaker. Heat the beaker on a gauze over a Bunsen burner until the temperature of the iron 3 nitrate has increased by about 5 degrees centigrade. Stand the beaker on the printed sheet as shown in figure 2.1. Use a 10 centimeter cube measuring cylinder to pour 5 centimeter cube of aqueous sodium thiosulfate into the beaker, and at the same time start a stop clock. Use the thermometer to stir the contents of the beaker. Look down from above the beaker, and when the text on the beaker, printed sheet becomes visible, stop the stop clock. Use the thermometer to measure the temperature of the solution when the text becomes visible. Rinse the beaker and the thermometer with water. Experiment 3. Repeat experiment 2, this time heating the aqueous iron 3 nitrate until the temperature has increased by about 10 degrees centigrade. Experiment 4. Repeat experiment 2, this time heating the aqueous iron 3 nitrate until the temperature has increased by about 15 degrees centigrade. Experiment 5. Repeat experiment 2, this time heating the aqueous iron 3 nitrate until the temperature has increased by about 25 degrees centigrade. Use the thermometer diagrams and stop clock diagrams to complete table 2.1. Here we are having table 2.1. In experiment 1, there is a stop clock diagram. You can see the seconds and minutes here. So this one must be the 1 minute. This must be the seconds. This must be the second. We have 5 seconds here. And what about the minutes? Here we are having minutes. These are seconds, minutes. So we have 1 minute. 1 minute means 60 seconds. Now in experiment 1, what the stop clock diagram shows, we have 60 seconds plus 56. 1, 51, 52, 53, 54, 55, 56. So time taken for the text to become visible in seconds, 60 plus 56. 60 plus 56. What we will get? We will get 116. What about the thermometer diagram? Thermometer diagram shows 20.5 degrees centigrade. So I will write 20.5. Experiment 2. If you look at this, you have 1 minute, which means 60 seconds, plus 15, 16, 17, 18, 19, 20. So I will write 60 plus 20, which means the time will be 80 seconds. What about the temperature? It's 25, 26, 27. It must be 27 degrees centigrade. Experiment number 3. Again, we are having 1 minute, which means 60 seconds, plus 1, 2, 3, 4, 5, 6, 7, 8, 9. 60 plus 9, which means total second will be 69. What about the temperature? It's exactly 30 degrees centigrade. Experiment number 4. It's less than a minute. What about the second? 45 second, 46 second. So we'll write 46 second here. What about the temperature? 35, 36, 37, 37 degrees centigrade. Experiment number 5. Again, it's less than a minute. So seconds. So we have 15, 16, 17, 18, 19, 20, 21. So we have 21 seconds. What about the temperature? 45, 46, 46.5, 46.5 degree centigrade. B. Write a suitable scale on the y-axis and plot your results from experiments 1 to 5. On figure 2.2, draw a smooth curve of best fit. So time taken for the text to become visible in seconds. I'm reducing the size. So here's a graph. On the x-axis, what do you have? You have temperature of the solution when the text becomes visible per degree centigrade. So time taken for the text to become visible. On the y-axis, I'm taking seconds, like we have 20 seconds here. Then we have 40 seconds. Then we are having 60 seconds. Then we have 80 seconds. Then we have 100 seconds. And here we have 120 seconds. So, first time, 116 seconds, 20.5. So first we have 116 seconds for 20.5 degrees centigrade. So 20.5 degrees centigrade. Here's 20.5, 116. So it must be between 120 and 100. So 100, 100 and so we have 1, 2, 3, 4, 5. So it must be 110, 110, 112, 14, 16. 16 must be coming here. So this is the first dot. What about second? 80 second for 27 degrees centigrade. 27. 1, 2, 3, 4, 5, 6, 7. So this line 80. This spot must be here. Third one, 69 for 30 degrees centigrade. 69. So it must be 1, 2, 3, 4, 5. So here is 69. So there will be the third dot. Number 4, 46 for 37. 37. 1, 2, 3, 4, 5, 6, 7. 46. 42, 44, 46. What about the last one? 21 for 46.5. 1, 2, 3, 4, 5, 6. We have 46.5 and so 21. It must be here. 21. Now plot it. Join all the lines. You will get this. So this will be the line obtained. Let me draw it clearly. The first two. Okay. C. Deduce the experiment in which the rate of reaction is fastest. It's very easy. It should be experiment 5. D. Use your graph to predict the temperature of the solution when the text becomes visible after 55 seconds. Show your working on figure 2.2, 55 seconds. So first of all, look at the seconds. 55 seconds. It must be between 50. So here's a second, 55 seconds. Where we are having 50. 1, 2, 3, 4, 5. Here we are having 50. So 55 second. 54 is 55 second. So you will show your working here. Value of temperature. It must be 31, 2, 3, 4. 34.5. 34.5. So right here, 34.5. Moving to next part. E. Explain why wrapping the beaker in cotton wool after it has been heated will improve the accuracy of the results obtained. Definitely, it reduces heat loss. And temperature does not change or remains constant. F1. Explain why it would be an improvement to measure the volume of aqueous iron 3 nitrate in a burette rather than a measuring cylinder. Burette have higher accuracy than measuring cylinders. Part 2, suggest why it would not be an improvement to add the aqueous sodium thiosulfate using a pipette. The reaction will start while still adding sodium thiosulfate. Part G, suggest why the aqueous sodium thiosulfate must be added after the aqueous iron 3 nitrate has been heated and not before it is heated. Reaction will start at room temperature. Part H, describe how the results of the experiment would change when the experiment is repeated using a 250 centimeter cube beaker in place of 100 centimeter cube beaker. Explain your answer. So definitely there will be less depth to look through the text, and it also decreases the time. So decreases time, less depth. The depth will decrease, less depth to look through when the text becomes visible. Number 3, a student tests two substances, solution F and solid G. Test on solution F. Table 3.1 shows the test and the student's observations. For solution F, the student divides solution F into 3 portions. Here's table 3.1. There's a test 1. Do a flame test on the first portion of solution F, light green color. Test 2, to the second portion of solution F, add at 1 centimeter depth of aqueous sodium hydroxide and a piece of aluminum foil. Warm the mixture gently and test any gas produced. Effervescence was seen. The gas turned damp red litmus paper blue. Test 3, to the third portion of the solution F, add a 1 centimeter depth of dilute nitric acid followed by a few drops of aqueous nitrate. No change. A. Describe how to do the flame test used in test 1. You can use a wire or splint for carrying the substance into flame and put sample into blue flame. Use a wire or splint for carrying the substance into a flame. Put sample into blue flame. Next part, identify the gas given off in test 2. Look at the test 2. You can see the gas turned damp red litmus paper blue. If you look at the test for the gases, which gas turns red litmus paper blue? So we have ammonia. It turns damp red litmus paper blue. It must be ammonia. So what you'll write? You'll write ammonia. Ammonia or NH3. C. Identify solution F. Now, how you can identify the solution F? If you look at the test, they are testing In test 2, they are using aqueous sodium hydroxide and piece of aluminum foil. So which indicates, here's the test, these are the tests. You can see the test here. This test indicates the presence of nitrate ion. So you are having nitrate ion because this is a test. Add aqueous sodium hydroxide, then aluminum foil, warm carefully, ammonia produced. So it must be nitrate. What about other test? For the third portion of test, they are adding dilute nitric acid followed by a few drops of aqueous silver nitrate. So halide ions, this is the test for the halide ions. You see, these are the halides, chloride, bromide, iodide. In all these, they are adding dilute nitric acid followed by aqueous silver nitrate. So you don't see any white, creamy white or yellow PPT or precipitates. So halide ions are absent. Halide ions are absent. What else is there? If you look at the test, in the flame test, they are giving the light green color. Now, look at the flame test, which is showing light green. Oh, it's a barium, Ba2 plus. So it must be barium nitrate. Barium nitrate. D. State what would be observed if the student adds dilute sulfuric acid to another portion of solution F. Now, if the student will add sulfuric acid to another portion, it will definitely reacting with the barium nitrate, producing white precipitate. You can see here. Here's a test for the sulfate ion and with barium nitrate. Barium nitrate, when it's added with the salt or acid containing the sulfate ion, will give white precipitate. So you'll write what? You'll write white precipitate will be obtained. Test on solid G. Solid G is iron 2 carbonate. E. About 10 centimeter cube of dilute sulfuric acid is added to solid G. Any gas given off is tested. So you are adding dilute sulfuric acid. This is a reaction between, it's like a reaction between metal carbonate plus acid. So whenever you are having metal carbonate and acid, you will always see bubbles of fizzing. So you'll write bubbling of fizzing. Bubbling or fizzing. You can even write effervescences. Now, what these effervescences are? These are of carbon dioxide. So how you're going to test this carbon dioxide gas? Look at the test for the gas. Here's carbon dioxide. Here's carbon dioxide gas. It turns lime water milky. So you write lime water becomes milky, or turn lime water milky. Part F, to the product from E, aqueous sodium hydroxide is added dropwise until in excess. Observations, adding dropwise, observations in excess. You are having iron 2 ions here. So if you look at the test for the iron 2 ions from this list, here we are having iron 2 ions. Now you are adding sodium hydroxide. Aqueous sodium hydroxide, what is the effect? You will get green precipitate, which is insoluble in excess. Or it turns brown near surface on standing. So you'll write green precipitate. Insoluble in excess. Moving to next question. Question number 4. A metal polish is a mixture of 4 substances. The properties of these substances are shown in table 4.1. Here's table 4.1. Name of this substance: propanol, ethanoic acid, iron 3 oxide, silicon 4 oxide. Now, propanol is soluble in water and on reaction with dilute nitric acid dissolves. What about ethanoic acid? It's also soluble in water and dissolves in dilute nitric acid. Iron 3 oxide is insoluble in water but reacts when warmed to form a soluble salt with dilute nitric acid. Silicon 4 oxide, it is insoluble in water and there's no reaction with dilute nitric acid. Plan an experiment to find the percentage by mass of silicon 4 oxide in the mixture. Your plan should include how you will calculate the percentage of silicon 4 oxide in the mixture. You are provided with a sample of metal polish, dilute nitric acid, and common laboratory apparatus. So let's look at the marks for this question. It's of 6 marks. So you can have 6 points. So you can write any 6 from. So what you can write, you can take the known or weighted mass of polish in a beaker. I'm mentioning the name of the container here. Take a known or weighted mass of polish in a beaker. Next, you will add nitric acid to the beaker. Add nitric acid to the beaker. Heat or warm the heat or warm the mixture. Polish and acid mixture. Next, you will filter so that you can remove the insoluble silicon 4 oxide, silicon, and wash. Filter and wash the residue with distilled or deionized water. I am writing distilled water. Not with tap water because tap water contains impurities. Tap water. Next point, you can dry the residue and description of drying, which is silicon 4 oxide here. Then you will find the mass. Find the mass of silicon 4 oxide. Last point, then you can calculate the percentage. Calculate the percentage by dividing the mass of silicon 4 oxide. That's what you have obtained by the mass of polish, and then you will multiply it by 100 in order to get the percentage. That's all for this video. Press like and share my videos. For more videos, subscribe to my channel and press the bell icon.